Hello students and welcome to Lesson 1 of Unit 6 Part 1. In this lesson you are going to receive an introduction to linear functions. Our essential questions are 1. What is a linear function? And 2. How can I identify a linear function given its graph, its ordered pairs, or its equation? And you will learn to identify a linear function in all three of these representations. Now, before we start looking at a linear function, let's review a problem that we've seen from Unit 5 and then connect it to a linear function. So we're going to think and discuss the following situation. It says, let's pretend that next weekend it is supposed to storm. And let's say that the snow is supposed to fall at a rate of ½ inch per hour. Would this represent a relation or a function? Well, we know that this would represent a function. Now, think about how we know. We know because each input would have one and only one output. For example, if for no hours it has snowed, then there will be no snow on the ground. If it snowed 1 hour, there will be ½ an inch. If it snowed 2 hours, there would be 1 inch. If it snowed 3 hours, there'd be 1½ inches, and so on, with each input resulting in one and only one output. So how do we know? Each input has one and only one output. Now let's graph this relationship and see what pattern we notice about the graph. So we have 0 hours, 0 inches of snow. 1 hour, ½ an inch of snow. 2 hours, 1 inch of snow. 3 hours, 1½ inches of snow. And if we continue the pattern, there'd be 4 hours, 2 inches of snow. 5 hours, 2½. 6, 3, 7, 3½, 8, 4, 9, 4½, 10, 5, and we could continue. But if you notice, all of these points, if they were connected, would form a straight line because it changes at a constant rate of change, which you heard in the last unit. Here's the constant rate of change. ½ an inch per, which means multiply, hour. In other words, y equals 0.5x. We will learn in this lesson that anytime there is a constant rate of change, it will create a straight line on a graph, which is called a linear function. So our new vocabulary word today is linear function, and you can see right there in the word line. A linear function is a function whose graph forms a straight line. So just because it's a straight line doesn't mean it's a linear function. It has to be a function as well. So it is a function whose graph forms a straight line. Now, a linear function forms a straight line because it increases or decreases at a constant rate, which we will learn is called slope. In the previous unit, we just called it a constant rate of change. Now we're putting a word with it called slope, and that's the vocabulary term that describes a constant rate of change. Now, in today's lesson, we are going to learn to determine whether a function is linear or not in 3 different representations. In your guided notes packet, you have this graphic organizer on the front page of your notes, and you will have to continually go back to it as we fill in this graphic organizer. So to start, let's start with determining whether a function is linear if we're given a graph. If we are given a graph, we need to first make sure that it is a function. Now recall, how do we determine if a graph is a function? We use the vertical line test. So we're going to see, does it pass the vertical line test, and then does it make a straight line? So is it a function, and is it a straight line? So let's look at some examples. Here we see a graph, and we can see that if we drew vertical lines on our graph, that it only ever touches at one place at a time, and therefore it passes the vertical line test and therefore is a function. So function, yes. Now, does it form a straight line? Yes. So since it satisfies both those conditions, this is a linear function. Let's look at another example. Check and see first if it is a function or not. We do so by checking the vertical line test. Passes, passes the vertical line test, passes the vertical line test, passes the vertical line test, and you can see that at every position it passes the vertical line test and therefore is a function. Now, does it form a straight line? No. Therefore, it is a non-linear function. And we know that this is not linear because this is a quadratic function. This is y equals x squared, and that does not make a line. It makes a U shape. So while you are thinking about your graphs, parent graphs help you because if you see that it has a square, you'll know it's not a straight line. That means it's a U shape. Okay, let's look at this example. Remember, we're testing, is it a function and is it a straight line? Now, we have a vertical line here. If we pass a vertical line over it, does it only touch at one and only one spot? No, this is not a function. Is it a straight line? Yes, but it has to fulfill both of these qualifications to be considered a linear function. So even though this is a straight line, this is still a nonlinear function because it's not a function at all. This is the only, a vertical line is the only straight line that is not a linear function. Okay, check and see, is it a function? In other words, does it pass the vertical line test? Check. Yes, it does. Is it a straight line? Yes. So is it a linear function? Yes, because it fulfills both of those qualifications. This is a linear function. Now let's look at a horizontal line. Is it a function? Does it pass the vertical line test? Yes. Is it a straight line? Yes. So because it fulfills both of these qualifications, we would classify this as a linear function. Let's look at another example. Is this a function? No, because it fails the vertical line test. We see that our straight lines are touching in more than one location. Therefore, it's not a function at all, and also it's not a straight line. So this is a non-linear relation because it is not a function at all. We should have called, let me back up a second. We should have called this one a nonlinear relation as well because it did not pass the vertical line test. Now, let's determine whether a function is linear or not based on its ordered pairs. So our first option is we could graph the points and then use our strategies for graphing, but in my opinion, it's easier to determine if the ordered pairs form a constant rate of change or not. So let's look at this table and we'll test and see if it has a constant rate of change or not. Now the constant rate of change must be evident in both the inputs and the outputs. So here we see we went up by 1, we went up by 1 again, we went up by 1 again, we went up by 1 again. So we can see that the inputs do have a constant rate of change. Now, the outputs, we went down 3, down 3, down 3, down 3. So they also have a constant rate of change. So this is a linear function because the inputs and the outputs form a constant rate of change. And we will learn that that constant rate of change is that it changes down 3 every time the input changes 1. This is what's going to be referred to as slope later on. That's just a little preview. Okay, let's look at another example. Here in the inputs, we see it's going up 1, up 1, up 1, up 1. It's going down 3, down 1, up 1, up 3. So the inputs have a constant rate of change, but the outputs do not have a constant rate of change. So this is nonlinear. Now, each input does have just one output, so that does make it a function. So this is a nonlinear function. Let's look at the inputs and the outputs again to see if they have a constant rate of change. So we went up 3, up 3, up 3, up 3. Down 1, down 1, down 1, down 1. So there's a constant rate of change in the inputs and in the outputs. So this is indeed a linear function. We will later see that it went down 1 in the outputs every time the input went up 3, or the fraction negative 1/3. You don't have to worry about this right now. It's just kind of a preview to get you connecting to a future lesson. Let's check this one and see if it has a constant rate of change or not. So we went up 5, up 5, up 5, up 5. So the inputs do have a constant rate of change. We went down 6, down 2, down 2 more, and then up 2. So this is not a constant rate of change. So this is non-linear. Now every input does have just one output, so it is a function, so we'll call this a nonlinear function. Now, we'll use the same strategies if we have a set of ordered pairs. We'll just organize them into the input-output table. So we have the ordered pairs 3, 5, 5, 4, 7, 3, 9, 2, and 11, 1. And we can see we're going up 2, up 2, up 2, up 2. So the inputs constantly go up by 2. We went down 1, down 1, down 1, down 1. So the outputs constantly went down 1. So yes, this is a linear function. So remember, anytime that you have a set of ordered pairs, you can treat them like an input-output table, because an input-output table is just a way of organizing ordered pairs.